Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everybody. I hope you are enjoying our course Microcontrolling Start as Professional. If you reach here, that means you are not starting to be a professional anymore. You are a real professional. You can by yourself now do many applications. We already discussed a lot of basics, and now you can just go and grab some projects from the internet or from other resources and try to applying them, and step by step, by more training, you will be more and more professional. Now we are going to speak about analog to digital converter. That means we are going to do some real application using sensors. So this is module 9. By the end of this module, you will be able to understand how to convert between analog signals and digital signals, how to use analog digital converter ADC, which is a built-in device in our AVR at Mega 3.2. So let me just give a quick introduction about analog and digital. So analog input usually refers to some types of input signals which has a continuous value. So its value is continuously variable. It's vary with the time. Measuring analog input is very common requirements for embedded system because we are going to use the sensors. So what are sensors? Sensors are actually a converters which is used to convert physical signals to time varying voltage. So signals always will give voltage. In AVR microcontrollers and Arduino, most of the sensors are varying between 0 to 5 volts. So as you can see here, if I have, for example, a guitar which is giving sound, so the sound is actually an air pressure, it will go through the circuit and change to voltage which is varying by time. Then when it comes out of the circuit to the speaker, it will change again to air pressure. There are many types of physical quantities that we can measure around us. For example, the temperature, the force, the pressure, the sound, the position, the velocity, the acceleration, the oxygen concentration, biometrics, signal strength, battery charge. All of these actually are physical values which is varying by time. It's continuously varying, and we need to use a sensor to measure this value, and the input will be this value and the output will be voltage. There are main differences between analog and digital signals. So we can say always analog signals are continuous in both time and amplitude. They are considered as noise sensitive and cannot be manipulated by computers. Since our microcontroller is a computer, so it cannot deal directly with analog signals. That's why we need to convert them to digital signals, which are discrete in both time and amplitude. So they are discrete values, generally free from noise. Usually the noise in digital signals is very low, and of course they can be manipulated by the computers. But they have one problem, which is cannot exactly represent or reconstruct the analog signals, because we will take samples of the real signals and this will make us lose some data. To do the analog to digital conversion, we do a process which is called discretizing. Okay, so we do the process that's called discretizing. So it's to discretize a signal from its continuous analog form to corresponding digital approximation. So the digital is approximation because it's sampling. We use a device which is called analog to digital converters. So as you see, if we have continuous value like this sinusoidal waveform, just for example, so to convert it to digital, we take samples. So this signal 1, we take discrete samples of it. So value 1, value 2, value 3, value 4. The same applies for the red one. So we take samples of it. To understand discretization, let's look at this simple conversion procedure. Actually, the discretization can be referred to as levels. Let's consider we have a signal, an analog signal of course, which vary between two values. The values are V low and V high, so low voltage and high voltage. Usually in AVR and Arduino, V low is 0 and V high is 5 volt. Discretization, as I said, refers to the levels. So if we have an ADC, the ADC will receive from the sensors an analog value. It will discretizing it, so it will change it to levels. These levels are corresponding to the number of bits that this analog to digital converter ADC is supporting. Let's say we have a 2-bit converters. That means it can give 4 values: 0, 0, 0, 1, 1, 0, and 1, 1. So the values between VL and VH are going to be represented using 4 levels. Okay, from the previous one you see here, these lines are for the levels. So if the value is between 0 and 1/4 of VH, then it will be represented by 0. Above 1/4 up to half of the VH, it will be represented using 0, 1. Okay, so it will be represented using 0, 1. Above half of the VH, it will be represented by 1, 0 until it reach the 3/4 of VH. It will be represented by 1, 1. So as I said, it's levels between the range. If the range between VL and 1/4, the level is 0, level 1, level 2, and level 3. Okay, so this leads us to speak about one important thing, which is the resolution of the discretization. The resolution of an ADC is limited and corresponds to the number of bits within the ADC. So the resolution, if we have 2-bit converter, so if we have 2-bit converter and the signal is between 0 and 5 volt, what will be the resolution here? So the resolution is 1/4 of the maximum. So here between 0 and 1.25 volt, the result will be represented by 0. Above 1.25 volt, it will be 0, 1 until it reach 2.5. It will be represented above 2.5. It will be represented by 2, and then until it reach 3/4 of VH. Above 3/4 of the VH, it will be represented by 3. So we have 3 levels: 0, 1, 2, 3. Okay, so this is discretizing. Sometimes when we speak about digitizing, some people think it's just giving the value of volt in digital. No, it's according to the resolution of the ADC. Now speaking about Atmega 32, Atmega 32 has a built-in ADC. It's a 10-bit resolution ADC. It can be accessed using port A. So as you see here, port A is ADC 0, ADC 1 up to ADC 7. The pins of port A between BA0 to BA7 has another function, which is ADC input. So it is a 1024 discrete levels. Why? Because it's 10-bit ADC. So 2 power 10 is 1024. That means the range between 0 and 5 volt can be divided to 1024 levels. So as I said, port A pins are used to sense the input analog signals connected simultaneously. Of course, if you are using port A as ADC, you cannot use it as a digital board. It's only analog board. It measures voltage on the port A pins with reference to the ground. It can also measure relative voltage. So if we change the relative voltage using this one, A reference, so if we apply here another voltage, it will be with reference to this voltage. One important thing, whatever the value of reference, of course, as I said, it's usually between 0 and 5 in our applications. So the measured voltage should not be higher than the reference voltage supplied to the AREF pin. So this AREF pin, it's actually the reference voltage. I will speak about it very soon. So the voltage applied to any of the channels or any of the ADC input shouldn't be above the V reference. The measured voltage VM, if equal to 0, it's converted to value 0. If it's equal to V reference, the maximum, it will be converted to 1023. So this is the maximum value of 10-bit. And if it's above the A reference, it will continue to be 1024. Don't do that. Don't try to measure voltage higher than AREF, otherwise you will fry your chip and your microcontroller will be burned. As I said, the default is 5 volt. Now, how to control the ADC? Of course, using special registers. So we have ADC SRA, we have SFIOR, we have AD max multiplexer, and ADCH and ADCL. ADCH and ADCL are containing the value of the conversion. Okay, so the value of the conversion will be stored in these two registers, one for the MSB, the most significant bits, and one for the low significant bits. AD max, I will speak about it. It's called AD multiplexer register. This one is a special function register, and we have the control status register. Let's speak about them quickly, one by one. Okay, so for the ADC SRA, what is important, actually very important one, is ADN. So this bit number 7, is for enabling the ADC. So if the value of this bit is 1, the board A will work as ADC. It will not work as digital board. It will work as input for the ADC. ADBS0 and ADBS1 and ADBS2, they are beside the pre-scalars. Okay, so pre-scalar is actually a frequency divider. And one important is the ADSC, which is start AD conversion. So when I apply one here, I give one here in my program. That means I am telling the ADC to start the conversion, because the signal is continuously available on the pins. So when I want to read the value, I will give an order to the ADC to start conversion. So it will take the analog value and convert it to digital value. So these are the values of the prescaler. As you can see, this is the division factor. Okay, so how much I want to reduce the speed of the clock. I will tell more details about the prescaler when we speak about the timers. So if I write a code like this, ADC SRA equal to set 1 for ADN, and I set 1 for ADBS2 and ADBS1. So from here I use this set. Okay, so 1 1, and this will be remain 0, and I enable the conversion. So ADN equal to 1 with this enable, and as you see, the prescaling is 1 divided by 64. So the speed of the clock will be divided by 64. To start the conversion on the ADC SRA, I give ADSC1. Okay, so you know, you already know how to use these shifting things and the or equal. So this is interpreted as put 1 on ADSC in ADC SRA. Okay, so this will start the conversion. Now I do this masking between ADSC and ADC SRA, so that it will continue looping until the result is 0. So when this is 0, that means the conversion is finished. For SFIOR, they have different types of conversion. We will use the default one, which is the free running mode. That means we give 0 0 0 for this 3-bit in register SFIOR. One important register is the multiplexer. So multiplexer will decide which pin is the input. If we go back here, so as you see, we have one ADC which is taking signals from 8 pins, which are between ADC 0 and AD7. So how to choose which one is our real input for the one ADC using the multiplexing. Okay, so these are the values for multiplexing. Okay, so for MUX0, MUX1 and MUX2 will decide the channel. So if they are 0 0 0, it will be channel 0, and if they are 1 1 1, they will be channel 7. For 3 and 4, they are used for gain, and for REF S1 and 0, they are used for voltage. So actually, how to change the reference from the default one 5 volt is using these two, but we are not speaking about them now. I will speak about them in the example. Finally, the ADCH and the ADCL, they are hosting the value of the conversion. After the conversion will finish, the result of conversion, it will be 10-bit, so it can be stored in these two registers. We can choose if the start from only 2-bit and we use the 8-bit from other one, or the ADCL will take the 8-bit and ADCH will take 2-bit using the ADLAR in ADMAX. So this one is to decide how to shift to left or to right the value. To get the conversion result, there is one special variable which is ADCW, or simply ADC, which is a 16-bit variable which will contain the value which is stored in these two registers. Finally, you should know that ADC conversion takes sometimes it's between 65 up to 250 microseconds, which is equal to 1040 up to 4000 clock cycles at a 16 megahertz clock. The equation to get the value of the ADC is simply like this. So V reference is usually, as we say, the default is 5 volt or 5000 millivolt. We take the Vn, it will be multiplied by 1024, and the result will be stored in ADC. Actually, what we get in our program is the ADC. So to get the Vn, we need to use this equation. So as you see here, the V reference is divided by 1024, and then we multiply it by the ADC. This equation will give us the voltage. So this convert back from ADC value, which is 10-bit, to the voltage. So this equation will use in our program. Vn in millivolt equal to ADC output multiplied by 5000 millivolt divided by 1024, which is the step or the resolution of the ADC. If we are discretizing Q equal to Vmax minus Vn divided by 2 power n. So we are using 5 volts, so it's 5 minus 0 divided by 2 power 10. So it's 5 divided by 1024. So this is the resolution of our ADC, which is 10-bit ADC. So each step is 4.88 millivolt. So let's say our input is 1.34 volt. If we apply this equation, okay, so Vn 1.34 multiplied by 1024 divided by 5, we will get this value 274, or in hexadecimal 112. Okay, so if we want to convert back, it will be 1.33. So as you see, it's not very accurate. We always lose some data. Finally, as we saw previously, always we do the initialization using a special function. So we will use ADC initial, a function. In this function, we will always adjust the ADMAX, and we will enable the ADN and choose the prescaling values. So here we are giving all of them 1, so the prescaling is 1 to 8. To read the value, we will always use this function. So as you see, the output of this function is 16-bit and the input is 8-bit. Why is the input is 8-bit? Because actually it's simply the multiplexer for choosing the channel. Here we do AND to make sure that the input is only restricted to this 3-bit. Then we clear the bottom 3-bit before ORing. So this to make sure that we have all 1 1 1 1 1 0 0 0. We make AND with it to make all of them 0. Then we make all with the channel. So we will pass the channel to the function, and here it will be passed to the ADMAX. The ADMAX now using this will read the channel that it's passed to the function. Then we start the conversion by putting 1 on ADC SRA. We need to wait, so this loop is waiting as I explained before. Then when it's finished, it will jump to return, and it will return the value which is already stored in the variable ADCW. You can use also ADC without W, it's also working. So that's all the theoretical parts about ADC. We will do some examples. Please refer to the examples and they will help you to understand better how things is going on. Thank you for listening and see you in next video.